All right, sports fans, we're in section 6.6, the fundamental theorem of algebra, which really sounds important. But if I would quote you the fundamental theorem of algebra, you would look at me and go, say what? So, um, the more important part than the fundamental theorem of algebra is the corollary to the fundamental theorem of algebra. It says this, it says, including imaginary roots and multiple roots. That means we're talking about multiplicities. Remember when we talked about multiplicities? That's how many times something occurs as a factor inside of a factored form polynomial. But if we include the imaginary roots and the multiple roots, an nth degree polynomial has exactly n roots, which means the polynomial function has exactly n zeros. So if it's a fourth degree polynomial, it'll have 4 zeros. Now that's not always true, because if the multiplicities are higher, then we could have fewer solutions. I'll try to throw an example of something like that at you. Well, you know what? Here, I'll show you one. Um, Suppose I had x minus 1 to the third and x plus 2 to the seventh equals 0. Okay, now that's the factored form of a polynomial, right? Well, if I were to ask you what the zeros were, all of you would say, well, that's a 1 and a negative 2. Well, what's the multiplicity of the 1? Well, it's a 3, right? It says so right there. That's the degree of that particular factor. That's how many times it occurs as a factor. And then the negative 2 appears 7 times. It has a multiplicity of 7. Now, what's the degree of this polynomial? The degree of this polynomial is 10. You find that by adding the multiplicities together. Now, if we had any other imaginary solutions in there, which we don't for this one, then you would have to include them as well. Okay, now that's a completely separate issue from example 1, so don't get that confused. All right, example 1. I have a polynomial equation. I'm going to ask you to fill in this table. Now, if you understand from yesterday the idea of irrational solutions coming in conjugate pairs and imaginary solutions coming in conjugate pairs, well, then you'll understand this whole idea. Keep in mind, for this chart, we are assuming, I know you're not supposed to do that, but we are assuming that each solution has multiplicity 1. Okay, keep that in mind. We're not going to go with multiplicity 2 because that could really change things. So if all of the solutions have multiplicity 1, then the total number of roots has to agree with the degree of the polynomial. Now, if we know that the solutions, that's a big word, if we know that the solutions are rational and irrational, then how many of each can we have? Could we have 3 rational solutions and 0 irrational solutions? Well, sure we could, We could have, 2, 5, and 1. I'm not sure what they are. I'm not going to factor this thing. We'll do that in a different problem. But we could have 3 different possible rational solutions. Could we have 2 and 1? Right? 2 rational, 1 irrational. That's still a total of 3, right? The answer to that is no. And the reason is because irrational solutions come in conjugate pairs. How could you have one irrational solution without its conjugate pair? That's not possible. Okay, so I wouldn't have even written that one down. I wrote it down only because I knew I was going to cross it off just to prove a point. Could I have 2 irrational solutions and 1 rational solutions? The answer is yes, because this is a conjugate pair. Sorry, I'll write the word not in there so you understand from the notes it's not a conjugate pair, but this one is. So I do have two conjugate pair solutions. That leaves me with one. And those are the only two options for this degree 3 polynomial. I could have 3 rationals and 0 irrationals, or I could have 1 rational and 2 irrational. And that's assuming that I have multiplicity 1 on each solution, and that I know that we are only dealing with rationals and irrationals. Okay, next. Let's do the same question, but let's suppose I knew that the solutions were real and imaginary. Same exact one. So we said from the last example that it was 3 solutions. Guess what? This chart will look no different. These numbers over here have to only be even numbers because of the whole idea of conjugate pairs. You can't have an odd number in this whole column. You can have odd numbers over here, that's no problem. And when you take this one and add them together, you're supposed to get that one. This one and this one added together, and you're supposed to get that one. So it works no matter whether we're talking about rational and irrational or real and imaginary. Now we could have bigger charts. We could talk about 5th degrees and 4th degrees, and then you could fill those charts out, which I'll have you do in class. Example 2 says, find the number of complex zeros of this. The number of complex zeros in example 3. Oh, sorry. I got my pages turned to the wrong lesson. Okay, so this is one where we probably need a hint, right? Okay, so if we know that negative 2 is a root, then we're going to use it, right? We talked about our synthetic division. X cubed, that's 1x cubed, plus 1x squared, minus 1x, plus 2. The only reason I'm putting the whole ones in there is just because it helps some of you to realize that it does have a coefficient of 1. If you already know that, then yes, you probably don't need to write that. We're going to drop down the 1. That's the very first step you do in all your synthetic division. Multiply these two together. Right? Multiply these two. And add down the column. Do the same thing. Multiply. Add. Multiply. Add. Okay, got a remainder 0. That's good. You better get a remainder 0. You were told it was a root. If you don't get a remainder of 0, something's wrong with your synthetic division, or you copied the numbers down wrong, or something like that. You could better go back and check what you got. Okay, so what are we left with? We got our remainder. We got our constant. We've got our linear factor. We've got our quadratic factor. So this is 1x squared minus x plus 1. So we have factored this thing into this, and we already knew it had an x plus 2. And the only way we can see what happens here, x plus 2, well, we know that you get negative 2 out of that, but that's obvious because we were told that in the beginning. This other one is a quadratic, and the only way I can find out when the quadratic will equal 0 is by using the quadratic formula. Opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And that gives me 1 plus or minus the square root of 1 minus 4 is negative 3 over 2. Do you see it? I see it. Yeah, that's an eye joke. All right, so it comes from the Apple Corporation. 1 plus or minus I square root 3 all over 2. There you go. You got them. How many solutions did we come up with? 1, 2, 3. So that means we've got 3 solutions. Well, that kind of makes sense. We had a third degree polynomial, didn't we? So that's why we know that there are 3 solutions. And these are the solutions that we had. Okay, we'll talk more in class.